The goal of physics is to be able to predict how systems will evolve given that they start out in some certain initial configuration. In classical physics, this evolution is found by using what are known as the equations of motion of the system. But how do we find these equations? The original equations of motion were given by Newton in the form of his second law. If an object has a momentum p and it has a total force F acting on it, then the change of the momentum with respect to time is equal to this force. If the mass of the object doesn't change, then we can find the acceleration of the object by dividing the force by this mass. Newton's second law works wonders, but the problem is that as systems become more complex, the forces acting on the bodies involved and the accelerations experienced can be difficult to keep track of. Luckily, there's a much simpler way of deriving the correct equations of motion known as the method of least action. As the name might suggest, this method uses a mathematical object called the action, which is a functional that depends on the time-dependent paths of all of the particles that make up the system. Just like how a function takes in a number or a set of numbers and spits out another number, a functional takes in a function or a set of functions and spits out a number. This means that typically functionals are written as definite integrals that involve the input functions. In the case of the action, the integral is over the range of times that one is interested in. But what goes inside the integral? This is a function known as a Lagrangian, which typically depends on the paths that the particles take and the time derivatives of these paths. We will talk a little more about the Lagrangian later. Okay, so we have an idea of what the action is, but you may be asking, how do we get anything having to do with physics out of it? Well, the original idea comes from what's called Fermat's principle. Consider we have light traveling through two different media, and the light travels at different speeds in these two media. Fermat's principle tells us that the light will not take the path of least distance through the materials, but the path that takes the least amount of time. Using this principle, one can find the reflection and refraction properties of linear ray optics. But how do we do this for more complicated systems? In a similar way, this is done in classical physics by finding the path which minimizes the action instead of the time. In calculus, you learn that the minimum points of a function occur only when said function does not change when the variables that the function depends on are changed by a small amount. Similarly, the action is minimized only when it does not change with a small variation of the paths that the action depends on. Sparing you the full derivation, if we write this in terms of the Lagrangian, we get the Euler-Lagrange equations of motion of a particle, which are equivalent to Newton's second law. Okay, that's how we get the equations of motion once we know the Lagrangian, but how the heck do we find the Lagrangian in the first place? Well, it turns out that it has the fairly simple form, at least for conservative systems, of the net kinetic energy of the system minus the net potential energy. These are much simpler quantities to find than the forces and accelerations, making the so-called Lagrangian mechanics extremely useful. But hold on. If we're able to derive how physical systems evolve from the Lagrangian, it makes sense that it should have some sort of physical interpretation, right? But the kinetic energy minus the potential energy? What's the physical interpretation of that? Well, for a very long time, people had no idea. In fact, this form of the Lagrangian was found by backwards derivation from Newton's laws of motion. So basically, it was used because it gave the correct answer. Not very satisfying. Another question you may have is, how do the particles in the system know to follow the paths which minimize the action? In fact, the more you think about this, the stranger it gets. Since we're integrating from some initial time to some final time, it seems like the system at the initial time would need some information about the final state to be able to travel the correct path. Is this evidence that the future actually determines the past, or is there something that we're missing? As it turns out, the answers to both of these questions lay in the realm of quantum mechanics and come from the amazing Feynman path integral. So in quantum mechanics, instead of talking explicitly about how things move, it makes more sense to talk about the probabilities of the outcomes of measurements. To find these probabilities, we must first calculate probability amplitudes, which we then square to find the true probability distributions. Perhaps the simplest of these amplitudes to consider is one where we measure a particle at one point at some time, and then measure it again at a different point at a later time. How do we find this amplitude? We can use a method developed by multiple physicists in the early to mid-20th century, but completed by Richard Feynman in 1948. First, consider the famous double-slit experiment where we shoot electrons at a screen, and between where the electrons are emitted and the screen, we put a barrier with two small slits in it. The basic ideas of quantum mechanics tell us that we have to treat the electron as if it travels through both slits simultaneously. In other words, the total amplitude of measuring the electrons at some point on the final screen is given by the sum of the amplitudes of the electron traveling through either one slit or the other. This results in an interference pattern observed on the screen. When we add more and more slits, the same principles tell us that we have to sum up all of the amplitudes of the electrons traveling through all of the slits. However, if we get a bit carried away, we find that we eventually create so many slits that the barrier is completely gone. Now, we have to sum all of the amplitudes where the electrons travel to any point where the barrier used to be. But since the barrier is no longer there, there's really nothing special about that point. So we can put one of these imaginary barriers at every point between the emitter and the screen and achieve the same effect. The result of doing this is that we find the total amplitude by summing over the amplitudes of all possible paths that the electron can travel. This is much nicer than the minimized action since there's no single special path. All paths have the opportunity to contribute to the final amplitude. Again, skipping this somewhat daunting derivation, one can find that the total amplitude can be written in this form, or more typically written as an integral, where the fancy integration measure just refers to the sum over all paths x of t. Now let me explain what everything means in this expression. The capital N is just a normalization. It's a number to ensure that probabilities don't exceed 1. H bar is Planck's constant, a fundamental constant of the universe, and S is the action I was talking about earlier, the time integral of the Lagrangian. So we have an answer to the first question about the physical interpretation of the Lagrangian. It's what determines the amplitude corresponding to each individual path. To answer our second question, we need to get a better idea of how to interpret these amplitudes. If we focus on just a single amplitude, we can see that it has the form e to the I something times something else. Another thing that has this form is the hand on a stopwatch, where the something is how fast the hand ticks, or the frequency, and the something else is the time elapsed. So let's try to draw a direct comparison between these amplitudes and the ticking of stopwatches. Say we attach a stopwatch to the particle. The frequency is a fixed constant of the stopwatch, whereas the time which elapses as the particle travels from point A to point B is a path-dependent quantity. Similarly, the amplitudes are determined by h bar, a fundamental constant of quantum mechanics, and the action, which is a path-dependent quantity. So, let's by analogy identify the frequency of the stopwatch with 1 over h bar, and the time elapsed with the action. Then we can think of the amplitude of each path as the final orientation of the hand of the stopwatch, and then we find the final amplitude by attaching all of the stopwatch hands head to tail and draw an arrow from the first hand's tail to the final hand's head. We can see a good example of how this works by looking at the double slit experiment mentioned earlier. For simplicity, let's just consider the two paths through each slit instead of the infinite possible paths that the particles could take. So we want to calculate the total amplitude corresponding to finding the electron at any point on the screen after it travels through the slits. To do this, we will associate a stopwatch hand to each path the particle can take, find its ending position, add them tip to tail, and we have our total amplitude. Let's see this in practice. So the electron starts at some source, and it can traverse either the red path or the blue path. The stopwatch arrows corresponding to each path tick at the same rate until the path hits the screen, at which point it stops. Then, we attach tip to tail of the two stopwatch hands, draw a new arrow from the first tail to the final tip, and the length of this new arrow gives us the amplitude. Finally, we just do this for each point on the screen, and voila! Just as we should expect, we see an interference pattern on the screen where we have alternating bright and dark spots symmetric about the center. Okay, this is great and all, but as we established before, we have to take into account all possible paths. Now, neither my coding skills nor my CPU are quite up to the task of generating an infinite number of paths, so let's just take the double slit experiment and ramp it up to say 100 slits. Now, let's just do the same thing as before. Let the particle traverse each path with the attached stopwatch, and as soon as it hits the screen at the point we want to measure, we stop the watch. To help keep track of things, all of the paths will be blue except for the shortest distance path, which will be red. So now that we have all of our final stopwatch positions, we find the total amplitude by adding the individual arrows head to tail and drawing the final arrow from the first tail to the final tip. Here we see something interesting. All of the paths far away from the shortest distance path swirl around each other, but the paths closest to the path of least distance tend to point in the same direction. With this in mind, let's remember our goal. We want to see how classical systems know to take the path that minimizes the action. In this case, the path that minimizes the action is just the red path of least distance. So we begin to see the answer to our question. When the stopwatch hands swirl around each other like they do for paths far from the red path, they don't really contribute to the total amplitude, since they don't add much length to the final arrow that we draw. On the other hand, the paths close to the red path all add up since they're pointed in roughly the same direction, which gives the dominant contribution to the amplitude. Recalling that these amplitudes are closely related to probabilities, our particle will be much more likely to travel a path close to that which minimizes the action than one which is far away. But we still aren't quite there. Close doesn't cut it because we know that in classical mechanics, particles exactly travel along the path that minimizes the action. So how do we see this in our stopwatch example? Well, remember that each individual amplitude depends on two things: the time it takes the particle to travel the path and how fast the stopwatch ticks. We've seen how the time associated to each path affects the total amplitude, but what happens if we start playing around with the speed of the stopwatch ticking? This is where things get interesting. Watch what happens when we take the same case of 100 slits and start cranking up the frequency of the stopwatches. The paths far from the red path begin to swirl around each other more and more tightly, meaning these contribute even less to the total amplitude. Even more, as the frequency increases, amplitudes from paths which started out pointing in a similar direction to that of the red path get pulled into these spirals, meaning that fewer and fewer paths actually contribute to the total amplitude. If we were to include all possible paths, we would see that when the frequency becomes infinite, the only contribution comes from the shortest distance path. Now, if we recall that this frequency corresponded to 1 over h bar in the definition of our path integral, we see something amazing. H bar is the fundamental constant of quantum mechanics. In essence, it tells us at what scales quantum mechanics should become important, similar to how the speed of light tells us what velocities special relativity becomes important at. To recover classical mechanics, we shouldn't see any effects from quantum mechanics, which means that h bar should be 0. However, taking h bar to 0 in our path integral is exactly the same thing as taking the stopwatch frequency to infinity in our analogy, and only the path which minimizes the action will contribute to the total amplitude. In other words, we've derived classical mechanics by taking an extreme limit of quantum mechanics. Let's take a moment to recap. We started out with two big problems that we wanted to try to solve using quantum mechanics. The first is that the form of the Lagrangian, kinetic energy minus potential energy, doesn't seem to correspond to anything physical in classical mechanics, despite giving the correct description for the motion of particles. The second is the fact that particles seem to know how to minimize their action before they undergo any motion. Our solutions to these problems came from allowing the particle to travel every path simultaneously, so the particle doesn't have to know anything about the path that it is taking. The form of the amplitude corresponding to the particle taking an individual path happened to be in terms of the Lagrangian, giving it a physical interpretation. Finally, we showed that when quantum effects are undetectable, the only contribution to the total amplitude comes from the path which minimizes the action, just as we would expect from classical mechanics. Now, as a final note, I will say that this analogy is not my own. It comes from Feynman himself and can be found in his lecture series titled QED, The Strange Theory of Light and Matter, which was published into an excellent book which I cannot recommend enough to anyone looking for an approachable introduction to the ideas of quantum field theory. You can also find the lectures themselves on YouTube, which I will link in the description. Feynman's path integrals are used all the time in quantum mechanics and are incredibly powerful in their ability to simplify calculations as opposed to more traditional methods. On top of being an incredibly useful tool, they also are one of the rare occasions that we actually gain insight into classical physics from quantum mechanics.